The purpose of the multipath and meteorological measurements experiment is to study the effects of multipath fading on digital systems, as well as evaluate various multipath countermeasure techniques and equipment. It is also intended to give the microwave system engineer a better understanding of the relationship between meteorological conditions and the clear air fading phenomenon. The information presented in this program is the result of a microwave testing program which has been conducted by Alcatel since 1982. The test hop studied here is located between Richardson and Kaufman, Texas, a distance of 29.7 miles. On the left, two spectrum analyzers display the signals received on the main and diversity antenna. The remainder of the display shows various meteorological parameters measured at the Kaufman site, including wind direction, wind velocity, temperature, and relative humidity differentials, and a plot of radio refractivity as a function of altitude. Meteorological data is recorded once each minute, but the information is displayed as a succession of 1-minute readings using time-lapse techniques. This procedure will allow us to cover 24 hours of information in just over 5 minutes. The sequence begins at 12 noon on April 26th and concludes at 11:59 a.m. on April 27th. The received signals from the space diversity antennas at Richardson are displayed on two spectrum analyzers. The upper display shows the spectrum from the main antenna, and the lower display shows the spectrum from the diversity antenna. The spectrum analyzers are operated in the normalized mode, displaying a straight line under non-dispersive conditions. The use of normalization allows a clear view of channel characteristics during flat or dispersive fading events. The vertical scale is 5 dB per division, and under non-faded conditions, the trace is 1 division from the top. Automatic level control in the down converters prevent fades of less than 12 dB from affecting the spectrum display. The horizontal scale is 4 MHz per division. This display shows a 22 dB flat fade. At the top of the screen is a 24-hour plot. The time is shown in hours and minutes. The time lapse is accelerated during non-fading events, that is 12 noon until midnight, then slows between midnight and 8 a.m. when most of the fading occurs. The upper right part of the display contains a wind direction indicator which shows the average wind direction during each 60-second measuring period. Below the wind direction indicator, we see the following display. On the left, wind velocity in miles per hour. In the middle, temperature difference in degrees Fahrenheit between the 10 and 260-foot sensors. And on the right, relative humidity difference in percent between 10 and 260-foot sensors. The radio refractivity is displayed as a function of height shown on the vertical axis. The measurements are made at 50-foot intervals between 10 and 260 feet on the microwave tower at Kaufman. The radio refractivity measured in N units is shown on the horizontal axis. The display range is 100 N units between 270 and 370. The computed values of radio refractivity as a function of height are shown in the center of the screen. This information was computed from measured meteorological data at 60-second intervals. Here we begin the presentation of measured data for the 24-hour period beginning at 12 noon on April 26th. The temperature and humidity gradients are very small during this time, which causes the refractivity to be very close to normal. That is, it has a slightly negative slope and is causing no propagation problems. When the time reaches midnight, 0 hours, the time-lapse rate slows considerably. During the time between midnight April 26th and 1 a.m. April 27th, the temperature gradient begins to build, but the humidity gradient is very small. This condition results in a 15 to 18 dB flat fade for the main and diversity receivers. Between 1 and 2 a.m., the main and diversity receivers experience a 25 and 12 dB flat fade respectively. Then, an out-of-band notch produces a 15 dB slope across the 30 MHz radio bandwidth. Here, the meteorological display is again slowed to aid our view, but the spectrum analyzers remain in real time. Between 2 and 2:30, the diversity receiver experiences a 20 dB notch on top of a 25 dB flat fade. Between 2:30 and 3 a.m., the diversity receiver has a 30 dB notch in band, which rolls out of band to produce a 10 dB slope across the 30 MHz bandwidth. From 3 to 3:30, the wind velocity slows to 0 miles per hour and remains there for over an hour. At this time, the main receiver experiences a 25 dB flat fade accompanied by a 30 dB notch, which gives a composite fade greater than 55 dB. At 3:30, the temperature gradient begins to grow significantly, and the refractivity begins to become more negative. The main antenna experiences a notch and flat fade, which combine to produce a total fade which reaches minus 80 dBm. Between 4 and 4:30, shifts in the refractive layers in the center of the path are causing 25 dB flat fades on both main and diversity receivers. The wind velocity remains at 0 miles per hour. From 4:30 to 5, the wind begins to gust and the humidity gradient builds sharply to 50%. Let's pause for a moment to take a closer look at this event. Shortly after 4:30, the wind begins to blow from the northwest. This moves the stratified air masses, which were formed in the past during the period of no wind, across the sensors mounted on the Kaufman Tower. This movement allows us to see the super-refractive condition, which has been causing flat fading of 20 to 25 dB for over an hour. Flat fading occurs when the main beam is bent downward by the negative refractivity gradient, allowing reflected signals to approach the magnitude of the main beam and cause significant in-band notches, a condition clearly seen in the following segments. Waves form on the interfaces of atmospheric layers much the same way waves form on the surface of a lake. These surfaces cause the magnitude of the reflected signals to fluctuate rapidly, as seen in the following segments. Between 5 and 5:30, severe superrefractive conditions exist, causing 20 to 25 dB flat fades on both receivers. The diversity spectrum illustrates the wave motion on the layered interfaces. From 5:30 to 6 a.m., the main antenna receiver experiences flat fades of 25 dB with additional 20 dB of slope. The wave action continues during this time. Between 6 and 8, the superrefractive condition continues due to lingering temperatures and humidity gradients. During this time, a very slow notch moves through the main antenna, reaching composite fades of 55 dB. Rapid spectrum fluctuations also continue at this time. Now, sunrise has caused a warming of the Earth's surface, causing a dispersion of the refractive layers. Our time-lapse is again accelerated between 8 a.m. and noon. The Earth's surface continues to warm, becoming a heat source once again. This reestablishes the vertical mixing within the atmosphere and disperses the temperature and moisture gradient that formed during the early morning hours. With this vertical mixing, the refractivity gradient returns to a normal condition, and the clear air fading previously observed on the received spectrums has ceased.